organizers for organizing this nice workshop in such a beautiful place. Yes, I was asked to present an introduction to the isomonodromy CFT correspondence, and this is by now a well-developed subject. Okay, so I would like to start with an example, which is a kind of probably historical motivation of the story, initial historical motivation. So the example comes from the two-dimensional statistical mechanics. So we consider the two-dimensional Ising model to be Ising model on the infinite square lattice. And so suppose we are interested in the spin-spin correlation function along the diagonal. So we put here a spin sigma 0, 0, 0, like somewhere here, spin sigma n, n, and we want to compute the two-point diagonal correlation function, which is going to be a function which depends on the separation of spins, of course, but it will also depend on a suitable temperature parameter T. So T is basically related to the true temperature and the Ising coupling constant. And there is a famous result by Jimbo and Miva, from the beginning of 80s, which says that, well, this two-point correlation function satisfies a particular nonlinear ODE. So more specifically, so if we introduce a function zeta of t equal to t minus 1, the derivative of tau n, with respect to t, and there is some correction minus t to the 4, then this function zeta of t satisfies the following differential equation. So t times t minus 1 second derivative squared equals to n squared t minus 1 zeta prime minus zeta squared minus zeta prime minus zeta and t minus 1 zeta prime minus zeta. So the form of the equation is not very instructive, but well, it has a name. So this is an equation which is equivalent to the so-called Painlevé 6 equation, or more precisely, this is basically an equation for the Hamiltonian of Painlevé 6, which is an non-autonomous Hamiltonian.
So for special parameters?
Yeah, for very special parameters and very special initial conditions, because basically this tau n, it depends only on this. There are no other parameters in the story. So maybe I should set more concretely. So if you know the Ising model, so this is something like sinh of 2j t minus 4, I guess. No, probably plus. Let me think. Where
Where is n?
plus.
Where is big N?
Sorry?
Where is big N?
Big N is in the equation, so
Oh,
it is here.
Okay.
So it appears as the parameter of the equation. Yeah, and on the other hand, there is a much older result, which is due to Onsager, Young, Motrol, Potts, Ward in the late 40s to early 60s, which relate the same correlation function, so tau n of t. So it can be written as a Toeplitz determinant. So it's a determinant of an n by n Toeplitz matrix. So Toeplitz means that all elements on the diagonal, on all of the diagonals coincide. So j, k run from 1 to n. And so these coefficients f, fk appearing in the matrix are Laurent coefficients of a particular function. So let me write it like this. So the sum with respect to...
Excuse me, why do you put a double vertical line for the determinant? I'm not understanding.
I can use whatever notation you want.
It's not telling me anything, is it? It's just
So this is just a matrix, just to tell you that it is a matrix.
jk element I have fj minus k.
Yeah. So your matrix will be something like this. So f naught, f naught, f1, f1, and so on. And you want to compute the determinant of this. And the fk's are the Laurent coefficients of the expansion of a particular function f, which is called the symbol, which, well, in this case, relevant to the Heun model, given by 1 minus z over square root of t to 1/2 and 1 minus z minus 1 over square root of t to minus 1/2.
Wait a second, just a second. So you don't have upper elements there? Is that a
No, I have all of them.
F
So I will have here f
minus n.
minus n.
Okay.
Yeah, and so this function has, I forgot to say that well, this corresponds to ferromagnetic region of parameters in the Ising model. So this means that so t will be greater than 1. So this means that this function here, if you look at it at the complex plane of z, so it will have branch points in here and here, and then so you can expand the function into Laurent series in this annulus, and so this gives you this fk. Right. But now, once you have this Toeplitz determinant, you can easily transform it into a kind of random matrix theory average. So you can equally rewrite tau n of t as something of the following form. 1 over 2 pi I to the n factorial, and then you have an n-fold integral with respect to complex variables, so z1 to zn, where you will have the product of zj minus n f of zj, and you will have a Vandermonde like zj minus zk squared dz1 dzn. Okay, so this is a really simple transformation. So you basically have to write every matrix element as an integral here, then transform the determinant of integrals into an integral, multidimensional integral of the determinant, and this anti-symmetrize and this expression. So this is called Heun formula for tuple determinants.
And you have zeta j minus zeta k, but you have
Sorry, yeah. So j minus j less than k. Yeah, and so this is where I come closer to the topic of this lecture. So you see that the multidimensional integral that we have here is actually a Coulomb gas representation of a particular C equal to 1 conformal block of Virasoro algebra. So something I will call F. So C equal to 1 you read from this exponent of Landermonde, and this conformal block will have, so this is a 4-point conformal block whose primary is allocated at 0, infinity, 1 over square root of t, and square root of t. So this already can be seen as a fun fact or a curiosity, at least, that you have a lattice model of critical, and its correlation function is given by a chiral Virasoro conformal block. Yes?
And the internal channel is fixed, right? Because we have given the
well, the internal charges, so you have the dimensions of primaries determined by basically what you have here in the function f, and you have conservations of momenta at the vertices, and so this n will also appear in yeah, but basically so what I want to stress here is that so on one hand we have a particular C equal to 1 conformal block, and on the other hand this gives a solution of Painlevé 6 certainly for special values of parameters and initial conditions. Yes?
So where do you read C equal 1 from?
Well, for C arbitrary, you would have something like 2 beta squared or 2.
But beta usually is epsilon 1 over epsilon 2.
Yeah.
This will be beta equal 1, and epsilon 1 equal epsilon 2 is not C equal 1.
I'm sure that this is.
Basically, it's minus 2 epsilon 1 by the epsilon.
Minus 2.
Ah, beta is minus 2.
Yeah.
Okay, okay. Minus 2 plus
Minus 2 epsilon 1 over epsilon 2.
Do you have any idea why C equals 1/2 became C equals to 1, or is that just irrelevant?
It's not even clear that how the conformal limit of our initial lattice model is related to this thing that we have.
It's not critical, isn't it? It's not.
This looks like a completely different story. Yeah.
So when you say solution of Painlevé 6, you mean solution of the sigma form of Painlevé 6?
Well, yeah. So this relation actually generalizes if you modify the symbol in a way consistent with the Coulomb gas formalism. So, for example, you can replace this 1/2 and minus 1/2 by arbitrarily complex parameters nu and nu prime, You can put here some additional factor z to the eta, but still, I mean, the corresponding Toeplitz determinant would be, on one hand, a C equal to 1 conformal walk, and on the other hand, one can show that it satisfies Painlevé 6. So this kind of results were obtained by people like Okamoto in the 80s. Okay, and so this is the relation that we want to understand and generalize. Okay, so now let us be more general and consider the theory of linear ODEs and their monodromy. I will focus on the simplest example of Fuchsian systems. Fuchsian systems, which are systems of the form d phi over dz equals a of z times phi. So this a of z can be, without loss of generality, supposed to be traceless. And for my purposes, I will stick to the case where it is a 2x2 matrix. And the word Fuchsian means that the form A of z dz, so this has only simple poles on the Riemann sphere. And, well, the simplest non-trivial case of this story corresponds to 4 poles that we can trace by a suitable Möbius transformation to 0, 1, t, and infinity, which means that our matrix A of z will be of the following simple form. So a naught over z plus a t over z minus t plus a1 over z minus 1. We will introduce a notation for the eigenvalues of this matrix residues at the singularities. So we will denote these eigenvalues as plus minus theta k, or k equals to 0, t, 1, and infinity, where so a infinity is minus sum of the 3 residues. Okay. So these are called local monodromy exponents. So the name comes from the following fact. So if we look at the general behavior of the fundamental solution of the system in the vicinity of these poles, we will see that so phi when z goes to let's say AK. So AK denotes one of those four poles. So it is given by a holomorphic non-vanishing matrix G K of Z multiplying Z minus AK to theta K minus theta K times a constant matrix over here. Right. And so now, once we have this, we are going to introduce, we are going to associate to this linear system two important spaces. So one space that I will call A will be the space of linear systems given by four tuples of matrices A0, AT, A1, A infinity, 2 by 2 and traceless, satisfying this. So the matrices should sum up to 0. We have to fix the spectra. Yeah, but I don't even introduce this this name, so I want to stay at the elementary level. And so I consider this this space of matrices considered up to conjugation in SM2C, because clearly if I start from the system, I can conjugate, say, this A by a constant matrix, and it will lead to a simple modification of phi. So I want to quotient by that.
I'm sorry, question. If delta K, like, can it be equal to 0?
It's better for them to be non-integer.
Okay.
Yes.
Okay.
So once again, so this is a subtlety which maybe I can comment later. So it's better to assume that theta k is not in 2z, but otherwise these are arbitrary complex numbers.
Why 2z?
1 half.
1/2.
It depends.
You don't want it to be half integer.
Yeah, 1/2. Yeah, you are right.
Yeah.
I have put 2 on the one side. Yeah. Okay, and so we can compute the rough. We can do the rough dimension count of the space. So the dimension of A. So we have 3 SL2 matrices. So 9 parameters. Now conjugation kills 3 of them. And fixing the eigenvalues kills another 4. So we have 2. So we can in fact parameterize almost any 4 tuple of such matrices with just 2 suitably chosen local coordinates, which you can choose in different ways that I will explain later. I want to say something more. Yeah. Now, given that my fundamental matrix solution is a multivalued function, I can associate to any such Fuchsian system another space, which is the space of its monodromy data. And the space M of monodromy data will be similarly defined as the space of 4 tuples of matrices M0, MT, M1, and infinity that multiply to the identity for which we also fix the eigenvalues, because you can easily understand from this local behavior that I have written somewhere, but maybe it just erased.
You wrote it there.
Here, yeah. So from this behavior, you can express this monodromy matrices instead of these constant matrices CK, called connection matrices, and thetas. But it is fairly clear that the eigenvalues of MK will be exponential to 2 plus minus 2 pi I theta k. And this, again, should be considered up to simultaneous conjugation, because, once again, we can choose a basis of solutions in a different way, and so this conjugation reflects that freedom. Okay, and completely similarly, we can notice that the dimension of M is equal to 2. And so now we can study the so-called Riemann-Hilbert map or monodromy map. So let's call this phi Riemann-Hilbert, which assigns to any point in here in A point in M. So this is a transcendental map, very complicated in general. Like, for example, if you consider systems of higher rank already, you have to, it's not clear whether, for example, this map will be surjective. If it is not surjective, its image, and so on. But for 2x2 systems, it is surjective. And so basically what we are going to be interested in is the explicit description of this Riemann-Hilbert map. Right. And in order to study this explicit description, first of all, I need to introduce indeed some suitable coordinates on these two sides over here. And I will start with monodromy first. So we can look, first of all, at special invariant functions on the space of monodromy data called trace functions. So if we have our four punctuates here, and we have some closed loop on the sphere, let's say gamma. So to this closed loop, we can associate a monodromy matrix M gamma, which will be a product of various powers of M0, MT, M1, and so on. And so the trace function is basically obtained by taking the trace of M gamma. Now, I can use that. And in fact, any such trace function can be written as a polynomial in number of generators given by the following basic ones. So first of all, we introduce k given by trace of mk, for k equal to 0, t, 1, and infinity. X equal to trace m naught times mt. Y equal to trace mt and m1. Z trace of m0 and m1. So it is, well, not completely trivial, but not very difficult exercise to check that you can express any such trace as a polynomial in terms of these 7 quantities. Now, this, as you can see, are related to local monodromies, 2 cosine 2 pi theta infinity. These 3 encode non-trivial monodromy data, and we have seen that well, the dimension of the space of monodromy data should be equal to 2. So this x, y, and z, they have to satisfy a relation, at least one relation. And so the relation is this. An affine cubic xyz plus x squared plus y squared plus z squared plus ax plus by plus cz plus d equal to 0, where this a, b, c, and d are some polynomials in pk. The explicit form is not so important for us, but so you see that we have in fact like 2 independent trace functions, and in principle we can, given a couple of trace functions, we can express our monodromy matrices in a unique way up to conjugation. Now, let me come back to this picture of the Riemann surface once more. So the trace function x, so this corresponds to the monodromy of our fundamental solution around the points 0 and t. You have y similarly related to monodromy, composite monodromy around t and 1, and the third trace function, well, you can imagine what it is. Right, and now let me introduce a special notation for x. So I will call similarly, so this sigma will be the composite monodromy exponent parameterizing the eigenvalues of this product. And so now if we look closely to this relation, by the way, this is called Friquet relation. Something from the end of 19th century. So if we fix in this relation x and a, b, c, d, so what remains is the following structure. So we have actually a quadric in y and z. And a quadric means that we can we can find a rational parametrization for y and z, which we can write in the following form. So we can parameterize y as a exponential to I eta plus b exponential of minus I eta plus c. Z similarly exponential of I eta plus b twiddle exponential of minus I eta plus C twiddle. So the A, B, and C here are related to thetas and sigma. And so this eta is a new coordinate which was missing, right? So we have then this sigma and eta, which are Fenchel, Nielsen type coordinates on M. So this pair of coordinates, as you may see, is associated with a particular decomposition of our two-punctured sphere in pairs of pencils. And now look, so far the parameter t, so the position of this fourth singularity, not fixed by Möbius transformation, it was just some fixed constant. But now we can ask the following question. So suppose that we want to have the monodromy fixed, but we will deform this parameter t and try to see what happens at the level of our Fuchsian system. So so the question is how to modify this A case in such a way that thank you very much. So the main message of the first part of the talk was that in order to solve the monodromy problem for linear ODEs or linear systems, Fuchsian, one has to construct functions like tau, one infinity, so this is what you need for Painlevé 6. And a function like so sigma with the same data over here for Heun. And the goal of the second part is to link this monodromy problem to conformal field theory. So the main idea has been already outlined in the talk by Alessandra. So basically what I'm going to do is to provide maybe more details. And also, if time permits, I will try to explain how the CFT predictions for these functions can be proved using Riemann-Hilbert technique. Okay, so let me start the third part. So monodromy of conformal blocks. So as we have seen in many of the previous talks, if you want to define Virasoro conformal blocks on this here, we need precisely this kind of data that we had over here. So we need a trivalent graph. Like this one. So this graph represents a particular Pence decomposition of the punctured sphere that we have. So just as above, we can put here the punctures. And so to each edge of this graph is attached a complex number delta, the conformal weight, the conformal dimension. So here we have delta naught, delta t, delta, and so on. And so basically what you do is that you feed this kind of data, the graph with all this labeling to, well, CFT machinery, or which is essentially the representation theory of the Virasoro algebra. And this gives you a certain multivariate.
Excuse me, I haven't understood what are the delta, the nabla case?
So for now, they are just complex numbers.
Okay.
So you can actually consider this CFT story like a black box which produces you, starting from this data, a certain multivariate series. Well, here it will be univariate, so let me add something else. So let me put here like Z, maybe Z1, Z2, Z3. So it will produce you a multivariate series in ratios like Z1 over Z2, Z2 over Z3, and so
So the delta are weights on each edge of the graph?
Yes, deltas are weights on the edge, all edges of the graph, and basically, so the coefficients of this multivariate series will depend on all these deltas and on the central edge of the Virasoro algebra.
Yes, sorry. So when you draw the tau function, what is the meaning of the graph in the case of monodromies?
Yeah, so this, maybe if you recall, so we have tried to parameterize the monodromy matrices in our punctured case in a certain way, and this way was related, just as in CFT, to a particular Pence decomposition. So this pair of monodromy coordinates sigma and eta was, so this pair was a kind of Fenchel-Nielsen type coordinates on the space of monodromy data.
Right, but it was something like x and y, right? X and,
not quite. So actually x was 2 cosine of 2 pi sigma, right? But these y's and the z were of the form of this form here, minus eta plus something else, where these guys were trigonometric functions of sigma and all of the thetas.
So x is related to the monodromy around 0 and t. That's
right.
That's
So x or sigma is the monodromy around a pair of points 0 and t, and theta is the corresponding twist.
Okay.
Right. And so if so what makes conformal field theory so efficient in various aspects is that, this multivariate formal series is expected to be actually analytic function of all of the variables. And moreover, global analytic properties of this function, they can be described using only elementary fusion and braiding transformation. So let me very briefly explain what these are. So suppose that you have, first of all, a 4-point conformal block with delta over here, some other deltas attached to external edges. So the singular points will put exactly as before. So this conformal block, which is basically a series in t variable, can be written in terms of conformal blocks like of this form here, infinity t1 delta prime. So this is a series. So this is a series in t. This is a series in 1 minus t, and these two series are related by an explicit transformation f delta prime. Then, of course, this matrix also depends on the other external dimensions. So delta t, delta naught, delta 1, delta infinity, and this is independent of, and we have to integrate with respect to internal dimension of the conformal block over here. So you can, if you have never seen this, you can think of this as being a generalization of the connection formula for a geometric function. So you have the element of one basis on one side and the element of another basis of solutions on the other side. So it's an infinite dimensional space. Okay, so this is the famous also Cashner formula. And now if we want to sort of consider monodromy properties of more complicated conformal blocks, it turns out that, well, basically we can add here anything we want. So any black box, provided we add the same black box over here. Okay. So you still have the very same transformation with the very same fusion matrix F. Right? And this becomes particularly handy when we start to study the monodromy of conformal blocks with respect to positions of degenerate fields. Because in this case, the sum that we have over here, sorry, the integral that we have over here becomes just a sum, right? So for example, if we have level 2 degenerate field, which I will symbolize by a dashed line. So dashed line means that we have a special dimension over here. So let me put here P21, P0, P1, P infinity. And yeah, maybe I have to establish the dictionary. So the central charge is 1 plus delta 6 q squared, q is b plus b minus 1. Deltas will be parameterized, so I will trade deltas for p's, or momenta. So deltas will be q squared over 4 minus p squared. Right, and so the main property of this degenerate fields is that we can only have two possible dimensions in the intermediate channel. So this is so if we consider this as a function of the position of the degenerate field, so we can rewrite the previous fusion relation which we had over here as so we have a sum with let me put here p naught plus epsilon b over 2 and say that epsilon is equal to plus or minus 1. So then this is necessarily the sum with respect to epsilon prime equal to plus or minus 1, and then it should be a linear combination of conformal blocks where we have this degenerate insertion on the other leg, P1. We have here two possible dimensions, P1 plus epsilon prime over 2, and here we have P naught and P infinity. Okay, and this holds with some matrix here, F epsilon P naught epsilon prime P1 P infinity. So this is basically what we get instead of this formula here. And so what is also important is that conformal blocks with degenerate fields, they satisfy linear differential equations in the positions of all the fields, so the so-called BPZ constraints. In this particular case, well, this BPZ constraint is a linear ODE, which is just the hypergeometric equation.
Sorry, Oleg, I'm a bit confused by reality properties of P. Is it imaginary in your
For now, everything is complex.
Okay.
Yeah. So it is just convenient for me to have, I understand that in Liouville you would like to have plus over here, but I do want to parameterize my dimensions. But later on, P will become purely imaginary. Okay, so this turns out a hypergeometric equation. So this object here, for example, is simply hypergeometric function 1 plus beta squared over 2 plus b epsilon naught 1 minus z 1 plus b squared over 2 plus bp1, and we have f1 of 1/2 plus b epsilon p naught plus p1 plus p infinity 1/2 plus b epsilon p naught plus p1 minus p infinity 1 plus 2 epsilon p naught. Oh, So this is an explicit formula for this particular 4-point conformal block. And as you may understand, so here F is nothing but the connection matrix for the hypergeometric equation. So where can I write it? So F of P1 P infinity is equal to gamma of 1 minus 2b P naught, gamma of 2b P1 divided by a product of two other gamma functions plus P1 minus P naught plus P infinity and gamma of 1/2 plus B1 minus P naught minus P infinity. So this is the fusion matrix in this degenerate case. And here there is a technicality that I would like to at least mention. So we may change the normalization of the degenerate vertex operators here in such a way that this fusion matrix becomes trigonometric. So basically I have to introduce some Barnes functions over there, and then the expressions like gamma over here will become something like cosine of P1 minus P0 plus infinity. It will become clear why do I want trigonometry instead of gamma functions in a moment. So basically I want these connection matrices to be periodic with respect to momentum. Okay. So now, with this knowledge, let us now consider a more general than this one conformal block. So this will be a 5-point conformal block. One of whose legs is degenerate. And we will try to understand how this more complicated conformal block transforms as we move this degenerate leg on the Riemann sphere. So we start with something like this. Okay. So here we have P0. I take one of the possible intermediate dimensions in this channel. So let me put here P0 plus PB over 2. Let me put here some P. And then let us try to compute the monodromy of this object. So we have 0, T, 1, and infinity. We place our degenerate field at some point Z close to 0, and we want to compute the monodromy of this object when Z goes along this this closed path. So this is the path which was corresponding to the trace function of, okay, not to x but to y. Okay. So what do we have to do? Well, first of all, we can make a fusion transformation to move this degenerate leg to this leg over here. So here we have T. And we will also make a Bredian transformation so that this becomes a linear combination of two blocks. So we have here P21, and here we have P T plus or minus beta over 2, P naught over here, and P over here. So I do not write here, of course, explicit coefficients, but you can determine them from that fusion relation. Okay, so what you have to do is to take this gamma functions or cosines to move this to here. Sorry, and I wanted to make a further Bredian move, so I want to place my degenerate field over here.
Why is the orientation important?
Well, the orientation symbolizes, so this is basically like if you take, for example, this conformal block. So suppose that you want to analytically continue this to negative z. So you can use, for example, f21, but with the arguments z over z minus 1, or something like this. Okay? Right. So once we have this, we can move to the other leg. We can move down and write this combination in the following way. So it's again a linear combination of two conformal blocks, where here we have P, here we have P plus minus B over 2. Here we have PT, and here we have P naught. So the external dimensions every time when we make this fusion transformation, the external dimensions they do not change. Okay? And now we have to be very careful to see at so what happens next. So for example, this conformal block over here, let's take the sign plus over here, and let's try to move the degenerate leg around the singular, the puncture z equal to 1. Okay. So what will happen is that we will eventually have over here P plus B over 2. Here we will have again P to 1. Here we are going to have P1 plus or minus B over 2. And, well, here everything else is unchanged. So we have Pt and P naught. So this is the transformation of the conformal block with the sign plus over here. But we also have conformal block with a minus sign, which will contribute as V1, V21, P1 plus or minus B over 2, P minus B over 2, P and P naught. So we have a linear combination of 4 now. And yeah, probably I will indicate what happens over here So here we make another fusion transformation. Here we make a fusion transformation to move over here. We make a full braid around the points equal to 1, and another fusion, nothing else. Yeah, b squared f.
Why did you consider b squared? Because I'm guessing that next you want to go that way, right?
Well, this is, so b is kind of half turn, whereas b squared is like going 2 pi around the puncture.
Maybe it will be clear if on the first equal sign you put bf.
B.
You did a fusion and then this half braiding.
Yeah, sorry. Of course it is f, yeah. Thank you. Okay. And then we continue with this linear combination of 4 conformal blocks. Again, keeping in mind that doing this fusion transformation, elementary fusion transformation, the external dimension cannot change. So, for example, if you cut this part of this diagram, so this is going to transform into what? So we will have the degenerate leg, after which we have the dimension p plus b over 2. Here we have pt and p naught. Whereas here we can have 2 dimensions which are related to this one by shifts by 1/2 of b. So we have either p plus b or simply p. Okay. So this is the transformation corresponding to the first line. Now the second line gives us something similar. We need to have p minus b over 2 on this internal line, which means that over here we can only have p or p minus b, okay? Right, and so now our degenerate field can continue now easily all the way to its initial position on the leg associated to 0. So the only delicate point was this going around the puncture over here to notice this shifts that we have. And so in the end, the result of analytic continuation of our initial conformal block that we had over here will be a linear combination of conformal blocks of the following form. So we are going to have here p plus b, here p naught, here p naught plus or minus b over 2. We are going to have a contribution where we have p on the internal line and again p naught plus or minus b over 2 and p naught over here, and finally plus the same thing with P minus B for the internal dimension. P naught plus minus B over 2, P naught. With some coefficients of this form, like gammas or cosines, depending on the normalization you use. Okay, and even though I have started with plus over here, it is clear that if I add minus, so well, it will be again a linear combination of the same 6 conformal blocks that we have over here. Now, what does that mean? So now let us take okay, let me say it in this way. So we see that conformal blocks of this form with degenerate field of type 1 have an operator-valued monodromy with respect to the position of the degenerate field. But now, so this operator-valued monodromy will involve, on one hand, the trigonometric expressions of the form like exponential of 2 pi I b p, so this kind of expression. And on the other hand, we also have these shifts, right? The shifts of the internal momentum, which can be represented as exponentials of b dp. Now the crucial point is that this operator commute as far as we impose certain constraints on b. Namely, if b squared is an integer number. And so let us do the following. So basically what we want to do is to diagonalize these operators or this operator-valued monodromy by a Fourier transformation. Okay. So we can hope to diagonalize them simultaneously by Fourier transform. Okay, so what we are going to do now? So first, let's set the central charge equal to 1. So this means that the parameter Q is equal to 0, B is equal to I, sorry. And let's also set P to be equal to, let's say, I sigma, and so pk, so the momenta associated to external legs of my conformal block, let's call them I theta k.
What is 0? Q?
Q. Liouville.
Oh, because 2 will be...
This is B plus B minus 1. And so what happens, so in this notation, what happens to sigma when we shift P by B? Well, sigma is just shifted by 1, right? And so then, once we have this, so the translations shift sigma by plus or minus 1. And so now define a Fourier transform of this formula we introduce the functions phi plus minus of z, which are given by a sum with respect to n of the exponentials of I and eta. So here we are going to have theta naught, theta 1, theta infinity, sigma plus n. So I now use, so we have already traded the conformal dimensions for this momenta pk. Now we replace external pk by thetas and the internal p by sigma. Okay? And then we consider all possible shifts of sigma and this sum over n over here. So this is going to be a certain function of z, just a second, on the four punctured sphere. Yes?
The plus minus is the momentum you didn't play.
Yeah, sorry, I forgot to mention that. So this is theta naught plus minus 1/2. Right. And so now, given our knowledge of the analytic properties, so this monodromy properties of conformal blocks for arbitrary C, we can now understand easily what will happen to this object if you do this analytic continuation. So basically, the translations of sigma will give rise to contribution to monodromy, which is no longer operator valued, but just a C value. So let me write it like this. So sigma goes to sigma plus minus 1 will correspond to appearance of these factors e to plus minus I eta. And so this means that these functions phi plus minus, they have exactly the properties that we want from the fundamental solution of our 4-point Fuchsian system. so the usual non-operator valued monodromy as we continue this Fourier transform in variable z on our punctured sphere. And moreover, you can now see that the structure of the coefficients of monodromy matrices. So, for example, suppose I want to compute the elements of, let me not write this. So suppose I want to continue this phi line analytically along the loop that we used before. So along the loop over here. So here we do not need to go around this leg. We have no translations. And so as we compute the monodromy of phi plus minus of z, monodromy coefficients of monodromy matrix around 0 and t will be trigonometric functions of sigma. On the other hand, if we compute the same thing but now around a pair of points t and 1, so this is what we have just done at the level of conformal blocks. So now we are going to have the coefficients which have the form exponential of I eta plus exponential of minus I eta plus something else, where again, so these guys are certain explicit trigonometric functions of sigmas, of sigma and theta k's, which are determined by the fusion by these gamma functions of cosines.
Sorry, but the monodrome is still a 2 by 2 matrix, right?
Yes. So here, strictly speaking, I have constructed only one row or one column of fundamental matrix solution. There is a technicality here that I would like to sort of put under the carpet. So if I want the full fundamental matrix, I actually need to introduce two degenerate fields in the story. But let me just ignore this complication for a moment. Yeah. But still, I mean, even if you have just one column, it makes sense to speak about monodromy. This is what we do for, if you consider, for example, scalar differential equation, right? If you have some basis of solution psi1 and psi2, so we do analytic continuation, so we get psi1, psi2 multiplied by something, right? And so what we have computed is just this, when we take psi1 and psi2 to be this phi plus minus, okay? And so now, as you may well guess, so the notation was suggestive. So this sigma variable that we had as internal momentum in our conformal block. So this corresponds to eigenvalue of the monodromy along this cycle here. And, so the parameter that we have over here, eta, so it corresponds to this twist-like, Van Helmholtz coordinate. Okay. So we have a very precise map from the monodromy data to solutions of the Fuchsian system. In a way, we have already constructed the solution of the corresponding Riemann-Hilbert problem by doing this, by setting c equal to 1 and doing this Fourier transform. The only thing that remains to do now is to reconstruct from this expression the corresponding tau function, and the expression for the tau function is in a way even more simple. So the tau function associated to this monodromy data sigma and eta is given by the Fourier transform of the relevant c equal to 1 internal blocks.
So, is there a way to construct the solution of the linear system directly from this? Like y?
This is y. Unless I misunderstand the question.
Oh, because you're only taking the scalar stuff, yes. I mean,
Again,
no, I was
I'm not
thinking about it too, it was, no, it is fine.
So this is the generic solution to the linear system.
Yes.
To something that you are hiding under the carpet that you were explaining earlier.
Yes, so this is like half of the fundamental solution, one column. Okay. And basically, well, how do you go from the fundamental matrix solution to tau function? So one way is to sort of compute A of z in the form phi prime times phi minus 1. Then from this you compute A naught, AT, A1. From this you compute d log tau dt, and so on. But this is not actually the way how this formula is obtained. And this is another reason why you would like to have two degenerate fields in the story. So what you have is when you have another degenerate field over here placed in some point z naught, so you can use it. So this object over here now will have two indices, right? Two indices equal to plus minus. Okay, so this will give you the really the fundamental solution. But what characterizes this fundamental solution is its behavior as z goes to z naught. So basically, you are going to have the fundamental solution, which is normalized, for example, to be the identity matrix at z equal to z naught. And so another way to extract the tau function from phi, which is different from this one, is to expand phi around this normalization point. And what happens is that the tau function, more precisely the logarithm of tau function, appears in the coefficient, in one of the first coefficients of this expansion. But if you do the same thing on the CFT side, well, when you fuse these two fields, at some point you will have the energy momentum tensor, which will appear in conformal blocks. And this, well, gives you the derivative of this guy with respect to t. So this is how you how do you get the tau function itself, which is more simple.
So the zero is a different degenerate field.
No, you can take the same. Yeah. Okay, so we now have this formula, right? We can, of course, compute this conformal block order by order, so the expansion in T using the commutation relations of the Virasoro algebra. But as was mentioned in many previous talks, we have the AGT correspondence. Which provides explicit formulas for this series. So ultimately, we end up with an explicit series representation for tau associated to a given monodromy. So, namely, the statement is the following. The ultimate statement is the following. So the expression like this, so the Fourier transform, and then you have a double sum over Young diagrams coming from this supersymmetric localization. And then we have something like T to sigma plus n squared plus lambda plus mu times b lambda mu of sigma plus n over here. So this gives you a series representation for tau in terms of t, and the series is completely explicit in the sense that the coefficients that you have over here, they are factorized rational functions of parameters such as this composite monodromy. Sorry, I forgot that there is also the Fourier. The Fourier momentum. So explicit factorized rational expressions in sigma and thetas. Yeah. Okay. So.
Also the Barn, right?
Okay. So I wanted to avoid this. Yeah. So in addition to rational expressions, you have some Barnes functions coming from. Actually, you should also have them over here, right? Because I have changed the normalization of my vertex operators. But up to this Barnes function prefactor that I wanted to hide or didn't want to mention. Yeah. So this is these are very simple expressions. Okay, so I think my time is almost up. So what can I say in the remaining few minutes? So okay, one point is that once you have this final answer, it can actually be rigorously proved using the Riemann-Hilbert approach. So the series can be proved, and the key object, the key quantity that has to be used here is the so-called Guidon determinant. Guidon determinant. So the idea basically is to transform the initial Riemann-Hilbert problem associated to the Fuchsian system to a Riemann-Hilbert problem on a circle with a certain jump given by relatively complicated hypergeometric expressions. And then to any jump matrix, one can actually associate this quantity here. And the important point is that there are variational formulas satisfied by this. So if the jump matrix smoothly depends on a parameter, then you have a derivative for this determinant, which allows you to relate this guy to the Jimbo-Miwa-Ueno definition of the isomonodromic tau function. But this is much more general. Okay? And then once you have this, this determinant, which is basically a Fredholm determinant with a kernel defined on vector valued functions on the circle, so you just expand it in the basis of Fourier modes in the sum of principal minors, and this is exactly the result that you get in the end. So if you just want to prove this formula, you can completely bypass CFT. Okay. And then, it should be clear that all of this very easily generalizable to a higher number of punctures, to like higher rank, to higher genus, to Q difference setting, and so on. So many people in the audience have contributed to develop all these things. Yeah. So let me conclude that. Thank you very much.